In this video, we'll study inequalities in basic probability theory. Now, we already know that probability of any event, PA, it is defined as number of elements in set A upon number of elements in sample space, and we know that any probability will always lie between 0 and 1, and that is the first and most basic inequality relationship in probability. So any probability must always lie between 0 and 1. Now, when we have two events, A and B, then we can always draw them on Venn diagram. Now, suppose this is A, this is B, and that's your sample space. Now, if we look at this region, A intersection B, we know that number of elements in A intersection B will always be less than or equal to. Now, this probability will always be less than A and will always be less than B. So, it will always be less than minimum of whichever is smaller, either NA or NB, and subsequently we can write probability of A intersection B will be less than or equal to minimum of probability of A and probability of B. Then the same way, if we look at A union B, now A union B is this entire region. Now we know that N A union B will always be greater than or equal to. Now it is greater than both A and it is greater than B. So it will be greater than whichever is greater of these two. Maximum of NA and NB, or we can write probability of A union B will always be greater than or equal to maximum of probability of A and probability of B. Now, there will be some questions where we'll be given PA and PB, and then we'll be asked to find minimum or maximum value of A union B and A intersection B. Now, we know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. Now, we know that probability of A union B, it is always greater than or equal to maximum of probability of A and probability of B, and it will always be less than or equal to PA plus PB. In the same way, we can write this condition for P intersection B. So we can write PA intersection B, it will be PA plus PB minus PA union B. Now we know that probability of A intersection B, it will always be less than or equal to minimum of PA and PB, and we know that maximum value of this probability A union B is 1, so it will always be greater than this PA plus PB minus 1. Now, if one event is subset of another, say for example, we have two events, A and B is contained in A, then number of elements in B is always less than or equal to number of elements in A. So basically, probability of B will always be less than or equal to probability of A. Then there can be inequality relationships in conditional probability also. Say for example, probability of A by B. Now we know that probability of A by B is probability of A intersection B upon probability of B. Now we know that in this case, probability of B, it must be greater than 0 but less than or equal to 1. Now if we divide A intersection B with any number whose value lies between 0 and 1 including 1, that means it will always be greater than or equal to probability of A intersection B. Now we can also define probability relationships in multiple events. Say for example, in case of 3 events. Suppose we have 3 events A, B and C. So we have 3 events A, B and C. Now this probability, which is probability of A intersection B intersection C, will always be less than or equal to minimum of probability of A intersection B, probability of B intersection C, and probability of C intersection A, and which is less than minimum of probability of A, probability of B, and probability of C. And in the same way, we can define probability of A union B union C, and it will always be greater than or equal to maximum of P intersection B, P B intersection C, P C intersection A. It is also greater than or equal to maximum of PA, PB, and PC, and this is clearly greater than maximum of this value. So there are many kinds of inequalities possible in basic probability theory. Now let us take up some questions. Now here the question is, for two events A and B, probability of A is 3 by 5 and probability of B is 2 by 3, then which of the following is or are correct? Now we know that P A union B will be greater than or equal to maximum of P and PB, because it is a superset, which in this case is 2 by 3. That means probability of A union B will always be greater than or equal to 2 by 3. Now we also know that any probability is always less than or equal to 1. So this value will always lie between 2 by 3 and 1. Now if we look at probability of A intersection B, it will be PA plus PB minus PA union B. Now if we look at PA plus PB, it will be 9 plus 10, 19 by 15 minus PA union B. Now we'll get this minimum value when PA union B is maximum and maximum value of PA union B is 1. So 19 by 15 minus 1 will be simply 4 by 15. So PA union B minimum value will be 4 by 15, and we'll get its maximum value when A union B is minimum, which is 2 by 3. So 19 by 15 minus 2 by 3 will be simply 9 by 15, which is 3 by 5. So that means this option C is also correct. Now we look at probability of A intersection B naught. Now probability of A intersection B naught is probability of A minus probability of A intersection B. Now probability of A is 3 by 5 minus probability of A intersection B. Now we are looking for its maximum value. Its value will be maximum when value of A intersection B is minimum. So P A intersection B naught will always be less than or equal to 3 by 5 minus 4 by 15, which is 5 by 15, that is 1 by 3. That means this option A is also correct. Now if we look at this option D is probability of A naught upon B. Now probability of A naught upon B is probability of A naught intersection B upon probability of B, or it will be this probability of B minus probability of A intersection B upon probability of B. So it will be 1 minus, now P intersection B will work out, and probability of B is 2 by 3. So it will be this 3 by 2 into probability of A intersection B. Now if we look at its maximum value, in that case we have to look for minimum value of A intersection B, and minimum value of A intersection B is 4 by 15. So it will be into 4 by 15, so which is 2 by 5. So it will be 3 by 5. So its maximum value is 3 by 5, And for minimum, we'll put this as 3 by 5. So there'll be 9 by 10 and 1 minus 9 by 10 is 1 by 10. So its minimum value will be 1 by 10. That means this option D is also correct. So all the 4 options are correct for this question. Now here the question is, let E, F and G be 3 events having probabilities 1 by 8, 1 by 6 and 1 by 4 and their intersection is 1 by 10. Then which of the following is correct? So we have 3 events E, F and G. So this is E, F and G. So let this be E, this is F and let this be G. Now it is given that probability of E is 1 by 8, probability of F is 1 by 6 and probability of G is 1 by 4 and their intersection it is given as 1 by 10. Then which of the following is correct? Now we know that probability of E intersection F will be less than or equal to minimum of probability of E and F, and in between E and F the smaller value is 1 by 8, so it will be always less than 1 by 8. In the same way, probability of F intersection G will be less than smaller value between F and G, which is 1 by 6, and the same way probability of E intersection G will be less than or equal to 1 by 8. Now if we look at probability of E union F union G, we know that this probability will always be less than probability of E plus probability of F plus probability of G. Now probability of E is 1 by 8, F is 1 by 6 and this is 1 by 4. Now this is 24, 3, 4 and 6. So it will be simply 13 by 24. So this probability of E union F union G, it is less than or equal to 13 by 24 and that's your option C. Now if we look at this probability, which is probability of E intersection F intersection G naught. Now probability of E intersection F intersection G naught is actually this probability. This probability is equal to probability of E intersection F minus probability of E intersection F intersection G. Now this is probability of E intersection F minus, and this probability it is 1 by 10. Now we know that probability of E intersection F, it is always less than or equal to 1 by 8. So its maximum value is 1 by 8. So it will always be less than or equal to 1 by 8 minus 1 by 10, which is 1 by 40. That means this option A is also correct. Now we look at this option B. Then option B is probability of E complement intersection F intersection G. Now it will again be probability of F intersection G minus probability of E intersection F intersection G. Now maximum value of F intersection G is 1 by 6. So it will always be less than or equal to 1 by 6 minus, and this intersection is 1 by 10. So it will be 4 by 60, which is 1 by 50. So that means this option B is also correct. Now if we look at this probability, which is E naught intersection F naught intersection G naught. So it will be this region, and this probability will be given by 1 minus probability of E union G union F. Now this probability will be minimum when this value is maximum. So it will always be greater than or equal to 1 minus 13 by 24, which is 11 by 24. So that means this option D is incorrect. Now the question is, probability of A is 1 by 2 and probability of B is 2 by 3. Now we know that P A union B is always greater than or equal to maximum of PA and PB. Now maximum of P and PB is PB. That means probability of A union B, it must be greater than or equal to 2 by 3. And we know that any probability is always less than or equal to 1. That means this option A, it is correct. Now if we look at A intersection B, we can write probability of A intersection B as probability of A plus probability of B minus probability of A union B, which is 7 by 6 minus probability of A union B. Now this value will be maximum when A union B is minimum, which is 2 by 3. So 7 by 6 minus 2 by 3, and there will be 7 minus 4, which is 1 by 2. So its maximum value will be 1 by 2 and will be minimum when we put maximum value of P A union B, which is 1, which is 1 by 6. So this value will lie between 1 by 6 and 1 by 2. So that means option C is also correct. Now we look at this option B. This is probability of A intersection B naught, and it is probability of A minus probability of A intersection B. Now probability of A is 1 by 2 minus probability of A intersection B. Now it will have its maximum value when A intersection B is minimum. Its minimum value is 1 by 6. So if we put 1 by 2 minus 1 by 6, it will be 3 minus 1 by 6. So it will be simply 1 by 3. That means this option B is also correct. Now the same way we can write probability of A naught intersection B. Now probability of A naught intersection B, it is probability of B minus probability of A intersection B. Now probability of B is 2 by 3 minus A intersection B has two values, 1 by 6 and 1 by 2. Now we take 1 by 6, then it will be 1 by 2, which is its maximum value, and if we put 1 by 2, then it will be this 1 by 6. So that means all the four options A, B, C, D, they are correct. Now the question is, a number A is randomly selected from the set from 0 to 99. The number B is selected from the same set. The probability that number 3 to the power A plus 7 to the power B has a digit equal to 8 at its unit place. Now if we look at powers of 3, 3 to the power 0 is 1, 3 to the power 1 has 3 in the units place, 3 square has 9, 3 cube has 27, and 3 to the power 4 is 1. So these values, they are going to repeat after every 4 powers. Then the same way we look at powers of 7. 7 to the power 0 is 1, 7 to the power 1 is 7, 7 square has 9 in the units place, 7 cube has 3, and 7 to the power 4 has 1. Again we'll have these values repeated after every 4 power. Now it says we need to find the probability that the number has digit equal to 8 in the units place. Now we'll get 8 in the units place if we choose 1 here, and then correspondingly we have 7 here. If we choose 9 here and we take 9 from this, or if we choose 7 from this and we choose 1 from this. Now if we look at values of A, then out of these 100, we have 25 sets of 1, 3, 9 and 7 each. So probability of choosing this favorable A will be simply 3 divided by 4. And once we have chosen A, then B is automatically chosen 1 out of 4. So it will be this 1 by 4. So the required probability is 3 by 16, and that's your option D. Now the question is, for any two events A and B, which of the following is true? Now the first one is P A by B. Now we know that P A by B is P A intersection B upon probability of B. We are given that probability of B is unequal to 0. Now we can write probability of A intersection B as probability of A plus probability of B minus probability of A union B upon probability of B. Now maximum value of A union B is 1. So it will always be greater than or equal to probability of A plus probability of B minus 1 upon probability of B. That means this option A, it is correct. Now if we look at this option B, it is probability of A intersection B naught. Now probability of A intersection B naught, it is clearly probability of A minus probability of A intersection B, because it is that part of A which doesn't contain B. So there will be probability of A minus probability of A intersection B. So option B is also correct. Now if A and B are independent, then we can write probability of A union B as 1 minus probability of A union B complement, and this is 1 minus probability of A complement intersection B complement, and we can write this as 1 minus probability of A complement into probability of B complement. That means option C is also correct. Now what about option D? If A and B are disjoint, then we can write probability of A union B as probability of A plus probability of B minus probability of A intersection B, which in this case will be 0. So it will be simply this PA plus PB, and we cannot write it in this form. So the correct options are A, B and C. Now here the question is, if A and B are independent events, then prove that probability of A union B into probability of A naught intersection B naught, it is always less than or equal to probability of C, where C is an event defined that exactly one of A or B occurs. Now first we will define this probability of C. Now probability of C is exactly one of A or B occurs. So it will be this probability of A intersection B naught plus probability of A naught intersection B. Now this is probability of A into probability of B naught plus probability of A naught into probability of B. Now if we look at this left hand side, we can write this left hand side as probability of A union B into probability of A naught intersection B naught. Now we know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. So this probability of A union B will always be less than or equal to probability of A plus probability of B. So we can write this probability of A union B will be less than or equal to PA plus PB, and here since A and B they are independent, we can write this as probability of A naught into probability of B naught. Now it will be this PA into PA naught into PB naught plus PB into PA naught into PB naught. Now clearly PA naught and PB naught, they are less than or equal to 1, and if they are less than or equal to 1, that means this is less than or equal to PA into PB naught plus PB into PA naught, which is nothing but PC. So we have proved that probability of A union B into probability of A naught intersection B naught will always be less than or equal to probability of C if A and B are independent and C is an event defined that exactly one of A or B occurs. Now here the question is, consider a function fx equals x cube plus ax square plus bx plus c, where a, b, c are chosen by throwing a die 3 times. Now find the probability that fx is an increasing function. Now you find total number of ways of choosing a, b, c. Now for each of a, b and c we have 6 options. So total will be 6 into 6 into 6, that is 216 times. Now this function has to be an increasing function. Now it will be increasing if f dash x, which is 3x square plus 2ax plus b, it is greater than or equal to 0. Now this is always positive for all x when leading coefficient is positive and when discriminant is less than or equal to 0. So the condition that we have here is 4a square minus 12b should be less than or equal to 0, or when a square is less than or equal to 3b. Now we need to choose the values of a and b. Now if we take b as 1, then value of a can be 1. Now if we take b as 2, it will be 6. Now we can take the value 1 and 2. If b is 3, then a can take the value 1, 2 and 3. If B is 4, again it'll be 1, 2, 3. If B is 5, again we'll have 1, 2, 3. And if B is 6, value of A will be 1, 2, 3 and 4. So altogether we have these 16 cases, and in each case we can have 6 different values of C. So it will be 16 into 6. So this required probability will be 16 into 6 divided by 216. Now this is 36, which is 4 by 9, and that's your option C. Now here the question is, 3 persons A, B and C in order cut a pack of cards, replacing them after each cut. The person who first cuts a spade shall win a prize. Find the probability that C wins the prize. Now any person who is going to cut a spade is going to win a prize. So the probability of winning a prize, it will be, now we have 13 spades and total we have 52 cards. So probability of cutting a spade is 1 by 4 and probability of not cutting a spade is 3 by 4. Now C is going to win if A doesn't win, B doesn't win, and then C wins, or A doesn't win, B doesn't win, C doesn't win, again A doesn't win, again B doesn't win, then C wins in the next trial, and this sequence will continue up to infinite. Now it is nothing but a GP. So this probability will be this Q square P upon 1 minus Q cube. So that is the required probability. Now Q is 3 by 4, so it will be this 9 by 16. P is 1 by 4, and here it is 1 minus Q cube, which is 27 by 64. So this probability will be 9 upon 64 minus 27, and which is 9 by 37, and that's your option 2. Now here the question is, A and B throw a pair of dice. A wins if he throws 6 before B throws 7, and B wins if he throws 7 before A throws 6. And if A begins, his chances of winning is. Now A is going to win if he throws 6, and we get 6 if we have 1, 5, 2, 4, 3, 3, 4, 2 and 5, 1. So there will be this 5 by 36, and A not winning, it will be 31 by 36. Now in the same way, B is going to win if he or she throws 7. Now it will be 7 if it is 1, 6, 2, 5, 3, 4, 4, 3, 5, 2 and 6, 1. So this probability of B will be this 6 by 36, or simply 1 by 6, and B not winning is 5 by 6. Now we need to find the probability that A is going to win. Now A is going to win if A wins in the first chance, or if A doesn't win, B doesn't win, but A wins again in third chance, or A doesn't win, B doesn't win, again both of them they don't win, and then A wins in the next chance, and this sequence will continue up to infinite. Now it is nothing but an infinite GP. So sum of this GP is PA upon 1 minus PA naught into P B naught. Now probability of A is 5 by 36. Now this is, now PA naught is 31 by 36 and PB is 5 by 6. Now this probability is 5 by 36, and here it is 36 into 6 minus 31 into 5 upon 6 into 36. Now 36 will cancel. Now this is 30 upon 61, and that's your option 2. Now question number 22 is, a coin with probability P of getting heads is tossed until a head appears for the first time. If the probability that number of tosses required is even, this probability is 2 by 5, we need to find value of P. Now we know that if the number of toss required is even, then it should be either not head and then head at the second toss, or not head, not head, not head, and then heads at the fourth turn, or heads at the sixth term, and this series will continue up to infinite, and this probability must be equal to 2 by 5. Now we know that this is nothing but an infinite GP. So sum of an infinite GP is P dash upon 1 minus, now what is the common ratio? Common ratio is P bar square, and this is equal to 2 by 5. Now we know that complement of P is simply 1 minus P, and here it should be 1 minus P square upon 2 by 5. Now we'll use A plus B, A minus B. We'll get this as P 1 minus P, and then P 2 minus P, and this is 2 by 5. Now P and P will cancel. We'll get 5 minus 5P, and it will be equal to 2 into 2 minus 2P. So it will be 3P is equal to 1. So value of P is simply 1 by 3. And that's your option number B. Now here the question is, a covered basket of flowers have some lilies and roses. In search of rose, Sweetie and Shweta alternatively picks a flower from the basket but puts it back if it is not a rose. Now Sweetie is 3 times more likely to be first one to pick a rose. If Sweetie begins the rose hunt, and if there are 60 lilies in the basket, find the number of roses in the basket. Now we are given that Sweetie is 3 times more likely to be first one to pick a rose. Now suppose probability of Shweta picking a rose is P, then probability of Sweetie picking up a rose, it is 3P. Now since these two events are mutually exclusive and exhaustive, we'll get 3P plus P equals 1, or the value of P is 1 by 4. So probability of Shweta getting a rose, it is 3 by 4, and probability of Sweetie getting it is 1 by 4. Then the basket, suppose there are n roses and 60 lilies. Now probability of getting a rose, it is n upon n plus 60. Now we need to find value of n. Now if Sweetie begins this rose hunt, then probability of her winning will be, she gets a rose in the first time, which is n upon n plus 60, plus now she doesn't get it, so it will be 60 upon n plus 60. Shweta also doesn't get it, 60 upon n plus 60, and then she gets it in the third time, so it will be n plus 60. Now I'll continue up to infinite. So this is the probability of Sweetie getting a rose or winning the race, and this probability is 3 by 4. Now this is nothing but an infinite GP. Now we solve this GP, we can write this as A, which is n upon n plus 60 upon 1 minus R, and R in this case is 60 square upon n plus 60 square, and it will be equal to 3 by 4. Now we can write this as n into n plus 60 upon n plus 60 square minus 60 square, and that will be equal to 3 by 4. So it will be n plus 60. Now this is a plus b into a minus b, so it will be n, and then it will be n plus 120, and it should be equal to 3 by 4. Now n and n will cancel. We can write this as 4n plus 240, and here it will be 3n and 360. So value of n will be simply 120. So number of roses in the basket, it is 120, and that is the answer to this question. Now here the question is, a 6-faced fair die is thrown until 1 comes. Then the probability that 1 comes in even number of trials is. Now suppose the event that 1 comes, it is A, and 1 doesn't come, it is A complement. We need to find the probability that 1 comes in even number of trials. So for this probability, we have this case when first one, it is not 1, and then second one is 1, or first is not 1, second is not 1, third is not 1, but fourth is 1, and will continue up to infinite. Now probability of A naught, so not getting 1 is 5 by 6, and getting 1 is 1 by 6. Now this is 5 by 6 whole cube into 1 by 6, and will continue up to infinite. So this probability is nothing but an infinite GP whose sum is 5 by 36 upon 1 minus 25 by 36. So which is 5 by 11, and that's your option A. Now here the question is, a pair of dice is thrown. The total of numbers turned up on both the dice is 8. Then the probability that number then up on the second dice is 5 is. Now we'll get this sum 8 when we have 2, 6, 3, 5, 4, 4, 5, 3 and 6, 2. So this conditional probability that number on the second dice is 5, when the sum is 8, it will be this total case, which is 5, and second number on the dice 5 only in this one case. So this probability is simply 1 by 5. So this A, it matches with S. So A, it matches with S. Now the second one is, a box contains 4 white and 3 black balls. 2 balls are drawn successively and is found that second ball is white. Find the probability that first ball is also white. Now while drawing a ball, the first ball can be white, it can be red. Now it is white with the probability 4 by 7 and red with the probability 3 by 7. Now if first is white, then the next one could also be white or red, and here also it could be white or red. Now if first is white, probability that second is white is 3 by 6, and if it is red, this probability is also 3 by 6. If first is red, then probability it is white is 4 by 6, and it is red with the probability 2 by 6. Now we know that second ball is white. We need to find the probability that first ball is also white. So we'll take this case in the numerator and we'll take these two cases in the denominator. So this required probability will be 4 by 7 into 3 by 6 upon 4 by 7 into 3 by 6 plus 3 by 7 into 4 by 6. And this is 1 by 2. So this B, it matches with R. So B, it matches with R. Now it says, a biased coin with probability P is tossed until a head appears for the first time. If the probability that number of tosses required is even, is 2 by 5, then the value of P is. Now if it is even number of tosses, then it will be tail heads, or it will be tail heads, and this sequence will continue up to infinite, which is an infinite GP. So this series will be 1 minus P into P, 1 minus P cube into P up to infinite, and this is 1 minus P into P upon 1 minus P whole square. Now this probability is 2 by 5. Now we can write this as 1 minus P into P upon 2 minus P into P, and it is 2 by 5. Now P and P will cancel. We'll get 5 minus 5P will be equal to 4 minus 2P. So 3P equals 1. So value of P is simply 1 by 3. So this C, it matches with Q. C matches with Q. Now this D is, a coin whose faces are marked 3 and 5 is tossed 4 times. What is the probability that sum of the numbers thrown being less than 15? Now some of the numbers will be less than 15 if we have all 3's, or if we have 3 3's and 1 5. So these are the only 2 cases possible. Now for this first one, probability is 1 by 2, 1 by 2, 4 times. There will be 1 by 2 to the power 4, and here out of these 4, any one can be 5. So it will be this 4C1, and then 3 of them 3's and 1 5. So which again is 1 by 2 to the power 4. So it will be this 5 by 16. So this probability is 5 by 16. And that's your option B. And this is the answer to this question. Now here the question is, we have this set S, a subset B is said to be nice if sum of elements of B is 2, 0, 3. Now if we look at sum of all elements in S will be 1 plus 2 up to 20, and there will be n plus 1 by 2, and there will be 210. Now this sum will be nice if it is 203. That means we have to subtract 7 from this. Now in how many ways we can subtract 7? So it could be this 7 itself, or it could be this 1 6, or 2 5, 3 4, or it could be this 1 2 4. So these are the 5 possible cases where we can leave out 7 from the sum. So the probability that this sum is nice, it will be 5 divided by a total number of subsets that can be formed is 2 into 2 into 2, 20 times. So there will be 2 to the power 20, and that's your option D. Now here the question is, a hunter's chance of shooting an animal at a distance of r is a square by r square. He fires when r equals 2a, and if he misses, he reloads and fires when r equals 3a, 4a, and it goes on. If he misses at a distance of na, then the animal escapes. Find the odd against the hunter. Now in this question, hunter fires at 2a, 3a, 4a, and it goes all the way up to na. Or we'll simply say this r is equal to k into a, where the value of k starts from 2 and it goes all the way up to n. Now, hunter's chance of shooting an animal at a distance r is a square by r square, and his chance of not hitting the animal will be 1 minus a square by r square. Now what we'll do is we'll find the probability that the hunter doesn't hit the target and the animal escapes. The probability that hunter misses the target will be given by, he missed it at first place, 1 minus a square upon 2a square into 1 minus, he misses at a distance of 3a, up to 1 minus, he misses at a distance of na also. Now we can write this as this product, k varies from 2 to n, 1 minus a square upon k square into a square. Now this a square will cancel. So we write this probability as this product from 2 to n, k square minus 1 upon k square. Now we can write this as k minus 1 upon k into k plus 1 upon k. So we'll split this product in two parts, k from 2 to n, k minus 1 upon k into this product, k from 2 to n, k plus 1 upon k. Now if we look at this first product, when the value of k is 2, this is 1, 2, 2, 3, 3, 4, and goes all the way up to n minus 1 by n into, now here when the value of k is 2, this is 3, 2 into 4, 3, and goes all the way up to n plus 1 upon n. Now here all these terms will cancel, and in this case these terms will cancel. So here we'll get this as n plus 1 upon 2n. So the hunter is going to miss the target. This probability will be n plus 1 upon 2n. Now in this case we need to find odd against the hunter. Now odd against the hunter will be pt naught upon pt, which is n plus 1 upon 2n, and this is 1 minus n plus 1 upon 2n. So it will be this n plus 1, and here will be this n minus 1. So this odd against hunter will be this value, and that is the answer to this question. Now the question is, a player throws an ordinary die with face numbered 1 to 6. Whenever he throws 1, he gets an additional throw. We need to find the probability of obtaining a total score n. Now first is when the value of n is 5. Now if n is 5, this player, he can score 5 if he either throws 5 or he throws 1 followed by 4 or 1 1 3 or 1 1 1 2. These are the only possibilities. It cannot be 1 1 1 and 1 because after 1 he'll get another chance. Now probability of throwing 5, it is 1 by 6. Now this is 1 by 6 into 1 by 6. This is 1 by 6 cube and this is 1 by 6 to the power 4. So that's the required probability now, which is 1 by 6, 1 minus 1 by 6 to the power 4 divided by 1 minus 1 by 6. Now this is 6 to the power 4 minus 1 upon 5 into 6 to the power 4. That means this option A, it is correct and option B will be incorrect. Now if the value of n is 7, it will be this 1 6 or 1 1 5 or it will be this 1 1 1 up to 2. Now here we have 1 upon 6 square, 1 upon 6 cube up to 1 upon 6 to the power 6. Now this is 1 upon 6 square, 1 minus 1 upon 6 to the power 5 upon 1 minus 1 upon 6. Now this is 6 to the power 5 minus 1 and this is 5 into 6 30 upon 6 to the power 5. That means this option C is also correct. So the correct options are A and C.